Hello everyone, welcome to Arvind EduTech, and in this video we are going to understand the Bohr's quantization condition and its atomic model. Considering the Rutherford's experiment in his atomic model, Bohr explained the discrete spectrum released by hydrogen atom, and he said that electron cannot travel in any orbit, but it will travel only in some specific orbit. As the Rutherford's model, Rutherford said that electron can travel in any orbit. So Bohr explained that if it is traveling in any random orbit or in continuous orbits, then the spectrum released by hydrogen atom should be continuous. But we know that it releases discrete spectrum. So according to de Broglie hypothesis, that if the orbits are stationary, it should have the energy if it is has stationary energy state, then it should contain the integral number of de Broglie wavelengths. It means that orbit should be equal to the length of that orbit should be equal to n into lambda, where lambda is the wavelength and n is the principal quantum number. Okay, we can consider this equation number 1. We know that the formula of de Broglie's wavelength, that's lambda is equal to h upon mv. So now what we can do is we can compare them. So because 2 pi r, so this 2 pi r can be equal to nh upon mv, nh upon mv. And since we know that the angular momentum is equal to linear momentum into the radius of the circular orbit, so mvr can be equal to nh upon 2 pi, right, from the equation. So we get this quantization condition that the angular momentum should be equal to nh upon 2 pi, where we know that n is the principal quantum number. N shows the principal quantum number. H is the Planck constant, and pi, you know what's that. So only those circular orbit can be allowed in stationary state of electron in which its angular momentum is an integral multiple of h upon 2 pi. H upon 2 pi. H is a Planck constant. Its value is 6.3 into 10 to the power minus 34 joule second. So according to the Bohr, he said that whenever the electron makes a transition from a higher energy level to a lower energy level orbit, it always releases energy, or if the atom absorb energy, the electron moves from lower energy state to higher energy state, or lower energy state orbit to the higher energy state orbit, right? So let's see it in detail. That the postulate of Bohr's theory of hydrogen atom was first the nuclear concept. So he said the nuclear is a massive central core of the center, and the whole mass is concentrated in on the nucleus. Also the quantum condition, we saw that the only those orbits are possible where the angular momentum is equal to nh upon 2 pi. So we can say that the two things which were base of the Bohr's postulate was the Bohr's theory was the first is the Rutherford's atomic model, and the second is Planck quantum theory. And the concept of stationary orbits. So electrons are moving in a stationary orbit. He said the electrons are moving in a stationary orbit, and these orbits do not radiate energy. They do not radiate energy normally. They do not radiate energy. Also, the frequency condition, that he said that atom can absorb or it can emit energy. When it is going to, when the atom absorbs the energy, the electron moves from the lower energy orbit to the higher energy orbit. And whenever the energy, whenever the it wants to jump from the higher energy level to the lower energy level, it always emit energy. The tendency of electron is that it just want to go to the lower energy state. Once it gains the energy, it jumps to the higher energy orbit, but again after some time it releases energy and comes back to the lower energy state. And the famous frequency condition of the Bohr's atomic model was HF. You can consider the frequency is equal to E2 minus E1. This is the difference between the energy of two orbits or two states. This is also called frequency, Bohr's frequency condition. Bohr's frequency condition. So we know that the electrons are revolving around the nucleus. Nucleus contains some positive charges and electron have negative charge. So obviously there is some electrostatic force. So according to Coulomb's law, that electrostatic force will be K. Charge on the nucleus will be Ze, where Z is the atomic number. You know that what is atomic number? Atomic number explains how many protons are there in the nucleus. So this is the charge on the nucleus. The charge on the electron will be E upon their distance, that is R. Okay. So this is what? This R is the radius of the orbit. R is the radius of orbit. So we can say that this electrostatic force is equal to K Ze square upon R square. You can consider this as equation number 1. You must know that the K is electrostatic constant. Its value is 9 into 10 to the power minus 9 Newton meter square per coulomb square, right? So you can consider the equation number 1. Also, since the electron is moving in a circular orbit, so it must have some centripetal force which revolves the electron into a circular orbit. We know that the centripetal force is equal to, formula for the centripetal force is mv square upon r. So the question is, from where the electron gets this centripetal force? The centripetal force comes from the electrostatic force. So this mv square upon r is equal to k Ze square upon r square. Let's solve it and get the radius. So r will be equal to kze square upon mv square. So only r will be left because one r will be cancelled out. We can consider this as equation number, this we consider as equation number 1, and this we consider as equation number 2. And we know that the Bohr's quantization condition, the quantization condition L is equal to mvr, or this is equal to nh upon 2 pi. We have just derived it. So from here the value of R can be nh upon 2 pi mv, and this is equation number 3. From equation number 2 and 3 we can equate them because both shows the value of the radius of permitted orbit. So we will equate them. So it will be k ze square upon mv square is equal to nh upon 2 pi mv. From here we can get the velocity of the electron in that particular orbit. So v is equal to two pi k ze square upon nh. Okay, v will be equal to 2 pi k ze square upon nh. This is the velocity of the electron in the permitted orbit, right? And when we put this value of v in the equation number 3, so by equation number 3 we can get the radius of permitted orbit. This is n square h square upon 4 pi mk ze square. So what are the values here? N is a principal quantum number. N is the principal quantum number. H is the Planck constant, and value of Planck constant is 6.63 into 10 to the power minus 34 joule second. Value of pi is 3.14. M is the mass of electron, which is equal to 9.1 into 10 to the power minus 31 kg. Z is the atomic number of the substance. K is the electrostatic constant. And E, and the value of K is equal to 10 to the power 9 minus 9 Newton meter square per coulomb square. Also E is the charge on one electron, which is equal to 1.6 into 10 to the power minus 19 coulomb. So this is the radius of the permitted orbit in the Bohr's quantization condition. See, here most of the things are constant. H is the constant except n, which is a principal quantum number. All the values are constant. So it is very clear that the radius of the permitted orbit is proportional to the n square. Quantum numbers square. It is proportional to quantum number square. So for hydrogen, Z is equal to 1. And we take n is equal to 1 here first orbit. So we'll denote this by R naught. So that will be n square 1 square, so it is h square upon 4 pi square mkr e square. So now we can put all the values. 6.63 into 10 to the power minus 34 square, 4 into 3.14 into 9.1 into 10 to the power minus 31 into 9 into 10 to the power minus 9 into 1.6 into 10 to the power minus 19 square. So if you solve it, you will get approximately 0.53 angstrom. This is the radius of the possible radii of first orbit, radius of the first orbit for hydrogen atom, right? Also we can compute the speed of electron and in that in particular orbit. We can compute the speed of the electron in particular orbit. We know that v is equal to 2 pi k z e square upon nh. So for hydrogen z is equal to 1, so v can be 2 pi k e square upon nh. What we do, we multiply c to the numerator and denominator. We will get 2 pi k e square upon ch into c upon n. So this is also a constant. This is also a constant which is denoted by alpha, and it is a fine structure constant. This alpha is called fine structure constant. Alpha is fine structure constant. So we can write this v is equal to alpha into c upon v. Since these all values are constant, 2 pi k e ch, so it has a fixed value. So alpha is equal to approximately, we can take it 1 upon 137. So it means the velocity of the electron in any orbit is equal to 1 upon 137. This must be c into n, c upon n. So for the first orbit, the velocity of the electron will be c upon 137. 137 times less than the speed of the light. Similarly, the energy of the electron in a certain orbit is equal to 2 pi square mk square z square e to the in nth orbit. If someone asks you what is the energy of the electron in the nth orbit, so it can be explained by this expression, which is energy in the nth orbit is 2 pi square mk square z square e to the power 4. And here I have mentioned what all these quantities are. Like m is the mass of electron, k is the electrostatic constant, z is the atomic number, e is the charge on one electron, n is the number of orbit, and h is the Planck constant. So it is very clear that whenever electron makes a transition from the higher orbit to the lower orbit, it always emits some energy in terms of electromagnetic waves. And because of this, we can see some spectral series of hydrogen atom. So we have divided this series in some categories. Like first is the Lyman series. The Lyman series is the series of electromagnetic waves which is in ultraviolet region. Ultraviolet region. So whenever the electron makes a transition from any higher orbit to the first orbit, it releases some ultraviolet rays, and that is called the Lyman series. So jump from any higher orbit to the lower energy to the first orbit. Similarly, the second series is the Balmer series. This contains some visible light. So whenever the electron makes the transition from the higher level orbit to the second orbit. So in that condition, the energy released comes under the Balmer series. This is the only series of electromagnetic waves emitted by hydrogen atom which is visible. And then the third series is the Paschen series. In this series the radioactive waves comes under infrared region, and whenever the electron makes the transition from any higher level orbit like 4, 5th or 6th or 7th and so on to the third orbit, the emitted series is Paschen series, and that comes under infrared region. Similarly, for bracket series, this is also infrared region. P-fund series, that is also infrared region. So whenever the electron makes the transition of the on the fourth orbit from any higher orbit, the series of ultraviolet radiation is called the bracket series. Similarly, if electron makes a transition from any higher level orbit to the fifth orbit, the infrared radiation is called P-fund series. So these are the conditions. So you can see this diagram here. This you will also find in your textbook, that some energy level, you can see some energy gap between the first and the second orbit. So whenever the electron is making the transition from higher level energy state to the lower energy orbit, it is releasing some electromagnetic waves. So from any orbit to the first, it is Lyman series, which is ultraviolet region. These radiations are ultraviolet. Whenever the electron makes the transition from any higher orbit to the second orbit, it releases some visible light. Also, you can see the other series are from comes from the infrared region. So we know that the in nth orbit the energy of the electron is explained by this formula. So when we calculate through this formula, we find that the energy on the first orbit of electron is minus what 113.6 electron volt. In the second orbit it is minus 3.4 electron volt. In third orbit it's 1.51 electron volt, fourth 0.85 electron volt, and so on. So you can see that the energy is increasing from the first orbit to the other orbits. So what was the problem? What was the limitations of Bohr's theory? The Bohr's theory could not explain the atoms like which had so many protons or so many electrons. It is only applicable to the hydrogen like single electron atom. It did not explain why only circular orbits are possible but not the elliptical orbit. Also, it does not explain the further splitting of spectral lines in a magnetic field. Electron also exhibit wave property. Orbit of electron cannot be defined by the Bohr theory, right? So these were the problems with the Bohr's theory. And if you like the video, please subscribe us and see you in the next video. Bye bye.